So I want to talk about how do we go from big data to useful intelligence. And I want to start by asking a question. Has the greater amount of data that we now have led to better decisions in the world? I think the answer is somewhat questionable. Some cases yes, some cases no. It seems like it should have led to much more better decision making, but somehow that doesn't seem to have happened exactly as one would expect. So I wanted to talk about why that is and how we can fix it. So I think, as we were just hearing, a big problem is information overload. We have a fantastic amount of it. I mean, some of you might remember before the web, like me, right? It seemed like there wasn't much information out there. The problem was we didn't have enough information to work off. Now we've got too much. And there's a bigger problem. We're getting much more data. You know, you ain't seen nothing yet. We're going to be collecting data from all of our, we already are, health things. Everything we do in our lives is turning into a big data mesh. So today's big data challenge really is to go from available to accessible and to go from average to personalized. We don't want to know what the average answer is. We want to know what the answer is for me, for my situation. And how do we do that? What's the trick for managing to do that? Well, I think a big part of the help we can get for doing this is with computation, being able to compute things. And really, if you like, opening up computation for everyone, making it citizen computation so that everyone, even if they're not highly trained in math and things, can make sure that they get empowered by this. So what are the elements we need to make that a reality? Well, I think there are three based on the computer and one based on humans. So the three are high-level computation, actually being able to do computations at a high level on a computer, which isn't always possible. A language, so you can talk to the computer. You need to be able to interact with the computer at the best level possible. And also the data that in some sort of computable form, so you're ready to compute from it. And the fourth thing, which I'll come back to at the end, is the right human skills. Given that we now have this computing, can we get the right skills to be able to use it properly? And they're not necessarily the same skills as before the computation. Okay, well, I'm going to start by putting this all together, I hope. And you will see that we built something here called image identify. And you'll see it's identified me correctly as a person, which is a good start. And if I try and hold various objects in front of it, let's see what we can try here. I'm just seeing a walkie-talkie there. So let's see whether it comes up. Oh, binoculars, boxing glove, American lobster. Well, remote control. It's not totally honed on this. But you can see what we've got here is something that's identifying an image. It's managing to identify a beer glass. That doesn't seem too bad. And what I'm going to try and do is I'm going to try and tweet this. It might have tweeted the wrong thing there. Let's try and tweet that. And I don't know whether that came onto the Twitter stream, but anyway, if lucky, I managed to tweet that. The idea is I was trying to set up things. I wanted to show you all these things put together in a sort of fun way as to how you can use computation to build real things rather quickly. The most impressive thing about that is that we built it in a month. It's not perfect, as you see yet. But the point is there was a technology stack there to enable us to build something like that in a month. And the question is how? What is the stack that we need to enable that to happen? Well, the first thing is data ready for citizen computation. It's pretty weird, but a lot of the data out there, it's assumed that humans should look at. You know, an Excel sheet. Well, Excel sheet's great, but, you know, in the end, you don't really need humans to look at 20,000 data points. You need a computer to help you analyze it. So you don't set the data up for humans, you set it up for computers. And what you really want to achieve is that the knowledge consumer is able to generate knowledge. I've often called this Web 3.0. You know, in a sense, the consumer is generating knowledge from the computer is helping them generate knowledge. You don't just want the knowledge generated and handed to them. So, a few examples of this, some linguistic access. So how do you get to the data? This is using our Wolfram Alpha technology. I could ask something like, let's say, population of Manchester versus sheep in France. And hopefully, if we're all wired up here, we got an answer there. And it turns out, sorry, it's gone a bit off the bottom of the screen, but there are 7.2 sheep in France and only 503,000 people in Manchester. But the point is, what's happened here is I put some query in, it went off, it analyzed the query, it turned it into a computer, it had computable data to work from, it then built the response live for me, it then produced a live document, pushed it out, and put it out to my machine. So that's not search. It's very different from search. That's computable knowledge, where we're taking knowledge, it's understanding the question and trying to compute a live answer for me. So essentially, it might never have been asked this question before, but it's computing it live. Here's another kind of example of how you interact with computable data. So this is what we call a knowledge app. This was part of a project we did for a Middle Eastern country where they wanted to analyze their own population for how their health worked. And you can actually ask it questions live. So if I'm 53, actually I'm a little less than that. So, and you know, if I have different characteristics, if I'm a smoker or not a smoker, what it's doing here is it's computing live in the document I have as my slideshow against all of the data, how I actually compare. It's doing that live. And that's an example of what you can do if you have computable data. It's doing it personalized for me. So a key question when you think about data is, what's the interface? Governments particularly often forget this. They say, oh, we put lots of data out, which is great, all for that. But the question is, how are you going to interface for it? Because the interface is a big deal. Jobs proved that with the iPhone, right? It makes a big difference if you have an interface with complicated stuff. And so those are two interfaces I've shown you, linguistic and sort of interactive, you might call what we call computable documents. But whatever interface you have, what's clear is the value of computational knowledge is way above the value of dead information. So we need to move our data from being this dead data ready for humans into live data ready for people, ready for computers. And if you think about where knowledge assets reside in the world, who has lots of knowledge assets? Well, there's corporate information. We've been doing a lot of projects with people with our Alpha engine privately to get their information exposed internally for them so they can query it in this linguistic way. Huge amounts of corporate information you can't get to because you normally look at reports. What you really want to do is linguistic queries often, or other ways to get to the data. You know, what was John's incentive in the last quarter for Spanish sales? I'd like to ask that. I don't want to look at a report and manually go through it. I want to know what the answer is to that. Publicly funded entities, particularly the BBC, huge amounts of data, you know, need to make it really accessible. Government. You know, governments often ask me, what's the biggest win from this modern era, potentially? And the answer is health. I mean, it's just by miles. It's a huge, huge sector. It's hugely inefficient in all sorts of ways, and there's huge technological innovation that we help to that. Automated assistance on diagnostics, you know, being able to deal with image processing, a bit like I was just showing, but instead of having highly trained professionals looking at images, let's screen most of them out with a computer. Let's improve the processes. There's a huge, fantastic amount that can be done with health, with modern technology, and the technology is only just getting there. Educational assessment, another place. And there are many other areas as well. And of course, ours. We have huge knowledge assets, and we shouldn't forget that. And of course, it's the combination of our knowledge assets, like I was showing that medical example, with the data that's out there that's really, really powerful. Well, another issue I brought up was, how do you talk to the computer? You need a high-level language, and you kind of need algorithms included. So we've been building just such a thing, and I thought I would try to show you that by writing a little app here, essentially. So what I'm going to do is I'm going to try and block my face. I thought you'd be fairly bored of seeing me by now. So I thought I'd try and get my face recognized so I can block it out. And so what I'm going to do is set me to be the current image. And then what I want to do is, let's say find faces and of me. And then what I want to do is apply a rectangle to that. And then I guess that's a graphics object. It's a bit early in the morning for this. So we will see what happens here. And what I guess I'd like to do is I'd like to show me at the same time as the graphics object. And let's see. Yes, there we go. I got myself blocked out. So with one line of code there, because I've got algorithms included, a high-level language, I can write very quickly an app which does something really quite complicated using very modern algorithms and so forth. So there you go. That's the last of my blocking the face out, I'm afraid. So this is our Wolfram language, which we launched about a year and a half ago. And it's literate, sort of multifaceted, algorithms included. And the real principle that's been going with this is the human trumps the computer. Make life easy for the human, even if it's harder for the computer. Computers are quite big beasts these days. They can cope fairly well, but human time is very valuable. Actually, this is part of a whole technology stack that we've been building for 27, 28 years at Wolfram. Originally, it was just for math, but now it's for computation, which is kind of what everybody does. And so there are many technologies. The language is in the middle, but we've also got cloud, and we're increasingly getting a hybridized cloud. So we want everything local. I think the future is not just the cloud. It's hybridized between local and cloud, depending on what you want to do. And so we've been building all these things and adding consulting in, and including private clouds, which are coming up thick and fast. People want a computation cloud to be able to do all these sorts of computations locally. So in a sense, what our company's been doing, is for computation to meet knowledge. We've been trying to apply computation everywhere, and including to as much knowledge as possible. And that was the Alpha project that was just mentioned. And our strategy, in a sense, is to build the ultimate ecosystem. So you can build everything you want with computation. You can push computation to the limit. I think we're only 10, 20% into what computation can do, but I think we can go a lot further. Now, as I mentioned, that's what we're trying to do to fix computing, so that computing works better with data, so that data can be more interpretable, so you can actually use the big data you have. In a sense, that's what I've been working on for many years from a technological point of view. Now, paradoxically, I think you need to fix the human as well. I say paradoxically because you'd think that if I'm saying, well, let's make the computers better, then I'm saying, well, that makes life easier for the human. Well, it does. But once you've made life easier for the human needs to go up to the next level. It's no use just pretending to be a computer anymore. You need to go up to the next level and act at a higher level. And so for a few years, I've been working on computer-based math, which is to try and reform education to fix up people so that they can interact better with the modern age. And the center of this is maths. Maths is a huge, big, compulsory subject through virtually the whole world's years of learning in school. And yet I think it's pretty largely broken. And I want to explain to you a little bit about why that is. I'm going to give you the very quick summary here. When you do math, the question is, what are you doing? And I think you're doing basically 4 steps. You're defining questions like this. You're translating those questions to math. So the question might be, if I go on talking for too long and this room is sealed, how long could you guys all survive? Okay, that could be a typical question. So I'm defining the question to be precise in some way. So the next thing is I'm translating it to maths. What does that turn into in this symbolic representation? Why do I want to do that? The reason I want to do that is because if I've translated it to maths, I can work lots of stuff out. There are hundreds of years of ways to work out answers from this sort of abstract representation. It's very useful having it in maths rather than just talking about it in English. And so then I might want to compute the answer. That means move from the question to the answer. And then I want to get the answer in this abstract form and turn it back into the real question. The answer is 3 hours, or it's minus 6 hours, in which case I probably made a mistake because it doesn't make any sense. So those are basically what you're doing when you are doing or learning maths. You're doing that process. You're running that process. Here's what's gone wrong. See, in education, we spend almost all our time doing step 3 by hand. But that's the one step that you can get computers to do fantastically better than any human. Instead, what we ought to be doing is getting humans to do much more of step 1, 2, and 4 and leave step 3 largely to the computer. And we can make a much higher level problem-based subject. Here's an example. It's a bit small, I'm afraid. You probably all had to do things like simultaneous equations at school, except that I've obviously set a variable to be something. So let me unset that and try again. Okay, so there was a thing you probably had to do at school. 2 simultaneous equations. Can you solve it for x and y? But the thing is, you probably didn't do this at school. Put a cube in there, and it's a bit harder. right? But actually, it's not that much harder. It's just the same idea. It's an equation. It just happened to work out harder, but the computer does that now. You don't really have to care about working it out. You just need to know how to deal with the answer. And in fact, it gets even worse than that, because potentially, network willing, I can talk to my phone. Solve x cubed plus 2 equals 2y, and y minus x equals 5. Now, Siri willing, we shall get an answer, and there is the answer. In all its glory, with graphics and everything else from our alpha answers from Siri. You've got to ask, if I can talk to my phone in 20 or 30 seconds and get an answer to a question that most people can't do after 10 years of schooling in maths, why the hell they're learning that in the first place, rather than spending their time on something more useful? The key thing that politicians, governments completely fail to understand is the following. If you remove the computer from maths education, you will remove most of the context. Why? Because maths wasn't that good at doing stuff before computers. It worked in some point cases. Physics, accounting, it didn't work for biology, it didn't work for mass data, there wasn't much mass data, etc., etc. Most of the areas where we use maths and computation today are because of mechanized calculating. If you pull the computer out of education, you will remove that context. You cannot do biology, you cannot do image processing, you cannot do most of the reasons for doing maths in the first place. So people are going to learn the wrong subject. And that's what's happening. Now, another question I get asked a lot is, how does maths relate to coding? Which is good that the UK in particular has introduced, got going on in schools. I think that's a great move forward. So the way I think about this is maths, in a sense, is a process for analyzing life, for analysis. And most people don't have that at all. They don't have that dimension of thinking because they went through all this hand calculating stuff. Coding, in a sense, is the way to express it. It's the way you write down your ideas about math and other things. So it's kind of like a language. So in fact, coding really should be part of math. It's a very crucial part of being able to express yourself. The big thing you've got to understand in education and in the world in general is you need to stand on the power of automation. What's wrong is to think somehow we should learn what all the machines are doing. This will never work. I don't really know how my computer works. I know more than some people, but I don't know in every detail how it works, but I use it. As machines get more layered, more automation gets, the thing is how to handle the automation, how to deal with the results of the automation, not how to know how to replicate it as a human. And that's what we've got to do crucially in education, but also elsewhere as we think about how to handle data. Now, don't compete with machines. In the end, good machines that have worked in history, humans have done a rather bad job of competing with, like trying to fly off a bridge instead of taking an aeroplane. Now, I wanted just to turn back to decisions for a moment and talk about instinct or analysis. So I think one of the issues with decisions is, if you like, before there was a lot of quantification, people tended to have fairly instinctual drives to decisions. You could argue it's a sort of pre-Thatcher era when there was fewer numbers around. And sometimes that actually resulted in pretty good decisions because people took a lot of data into account informally. Then we turned into this sort of thing where everything's a metric. There are 3 metrics to tell you how good this hospital is. And guess what? People game the metrics. If they're at all competent at managing things, they game the metrics, and then the metrics skew what you're actually trying to achieve. And so the question is there a sort of way of combining the quantitative of the metric of the modern era with the sort of instinct for making decisions? And I think there is. I think if you have the right interface to the data in sorts of ways I'm showing, you can have what I would call agile metrics, where you basically, you as the reader, you as the manager, you as the decision maker, are asking the question. The hospital or whatever it is producing the data set, the computable data set, but it doesn't know exactly what you're going to ask of that data set. You are making that decision because you've got the computing ability to be able to do that. I think that makes it much better able to avoid gaming and also more likely to be able to poke in different areas at the data and come up with some more real things. Now, of course, you do need to know what you're poking at and how to interpret the answers to make that work. So as I say, I think there are these eras of management from instinct to simple targets to agile targets and metrics, which I think we should be coming into. So it's worth thinking about what's tomorrow's sort of abstraction of knowledge, currency of knowledge, and value chain of knowledge. What are the things that will mark out people at the top of the value chain in the next 10, 20, 30 years? I don't think it's whether you can remember how to do long division. That doesn't seem very helpful to me. I don't think it's if you can remember facts by themselves, although facts can be important, but just the right facts in the right context. I think it's how to work with the automation in a meaningful way, how to feel comfortable with it, how to interact with it in the most beneficial way and know what's possible. Knowing what's possible, knowing the scope of what you can do is actually an incredibly important thing today because there's so much possibility. And just knowing that and knowing what the limits of things are, of automation things that you can do, is really crucial. So I have this phrase that I call the computational knowledge economy. It's kind of like Drucker and others in, I guess, the 50s, was it, said that, he talked about knowledge economies. It's a slightly vague term in many respects, I think. But I suspect what it really means is when most of the income of a country or whatever is based on people thinking rather than doing with their hands. Well, I think we're into the next era where it's to do with not just the base thinking, but how we think about interacting with the machinery we have. We've automated the hell out of computation, and that makes big changes in what kind of thinking. And so the next level up, the countries that will succeed will be sort of computational knowledge economy countries. And we need this new form of maths education, this new STEM education to be able to achieve that. It will really be a leapfrogging, a bit like universal education was, but in microcosm. So thanks very much. I hope you enjoy the talk. We like making everything computable, and hopefully it was that more than the other. I should also just finish by saying we've got a conference coming up in London in about 2 or 3 weeks on computer-based maths. So that's sort of hopefully make you go right to that extreme. Thanks very much.
So just to clarify, I guess, if for computer-based math, is it that you were going to teach no math whatsoever, or is there a certain threshold beyond which it doesn't really make sense?
Well, firstly, I would say computer-based maths is maths.
Yes.
So we're going to teach lots more maths and at a higher level. But I think your question is, would you learn no hand calculating at all?
Indeed.
Or just give it all to the computer? No, I think you learn some, and I think there are 2 reasons for learning it. So reason 1 is because you actually use it today. I still estimate things in my head, and particularly multiplying. People give me a bill for something, right? And I look at it and I say, well, there were 62 people, and they each got, but how did the bill come to this? And I do a rough estimation in my head. I still think that's useful. I could go and type it into a computer, but there are lots of cases where it's quite useful just to estimate. And that gives you some sort of easy verification, not the only verification. The other reason is because it really conceptually empowers you to know how to do it by hand. You've got to be very careful of this one. There's a lot of claim for that, where I think it's not the case. But I think there are cases where that's true. So I think early primary maths is mostly probably okay. By the time kids, if you take the UK, get to sort of 7 or 8 or 9, it's kind of going adrift. And by the time they're sort of 12, 13, it's just a completely different subject that they basically will never use, unless they become pure mathematicians interested in the history of hand calculating.
So what's the resistance? Because it seems one of these kind of logical things where you think, we're never going to use this stuff beyond a certain level.
So I think there are 2 main resistances. One is just educational inertia. Change in education is unbelievably difficult because you've got to get assessments right. And nobody wants to change the assessments before they know what they're doing, but then they won't change the subject of the assessment because they don't know if that's the right thing, and then there are teachers to change and everything else. So assessments, I think, are sort of a key to unlock this, and they're hard to get done because they're controlled by governments in most countries and so forth. I think the second thing is total confusion.
Okay.
So I thought when I started this that mostly people would be very hostile who had worried about this. Actually, what I found is they need to think about it. It takes people a few goes to think through, maybe this guy isn't a total nutcase on this. But when they have, it's mostly that they just never thought about the subject. It's like this God-given subject called maths that you've got to do. Right? It does good. It's good for your kids. It's good for you. It's good for you. But nobody really asked what it is. And if you listen to all the discussion about it, it's mostly about how you teach maths, not what maths is that you're teaching. And so it gets confused with the pedagogy. So I think those are the 2 major things I would cite.
So how soon will it be that we will see the shift, you reckon? Is it
Depends on the country.
Okay.
I mean, I think small, sort of as you go east and north, those sorts of countries, and some perhaps in Asia, react quickly to things, and things may change. And we already had Estonia starting on our computer-based maths, for example. you know, if it's larger countries like the UK, it all takes a bit longer to work through. The UK is funny, I think, politically, because you get everybody mumbling to each other about how what's being done is wrong. And they all figure it out. And then about, 5 years later, the politicians sort of work out, oh, we need to change. And suddenly there's a big change in the thing. The moment it's still a bit heathen to say you should stop people learning hand calculating, but it'll come. So I think, across the world, it'll take 20 years.
Okay.
But I think there's a much sooner horizon. And we need to push that. As the public, we need to push that in our countries. Get our children learning the right thing.
Cool. One quick question
Sure.
about your relationship with Apple and Siri.
Sure.
So when you talk into Siri now, how does it actually query? How does it work with Wolfram Alpha?
So what happens is Siri at the Apple end, so to speak, goes and translates my speech to text. So they're doing that. They're then deciding, is this a knowledge query? And if they think it is, they send it off to us and we send them back a result, and that's how you get it back.
Okay.
And it's pretty cool. We build the thing live and send it back. And so it's a little bit up to them, and it changes over time. Sometimes I do a query and I think, oh, no, that did get sent to us, and then that didn't. Actually, we've had a very long relationship with Apple. In fact, Steve Jobs was the guy who came up with the name Mathematica and was at our launch event in '88.
Wow.
And in fact, very early, I found a quote from him about how Mathematica would allow you to focus on the prose of mathematics and not the grammar. So actually, I look back and see he was very early on trying to reform math education.
Cool.
So
Fabulous.
great. Thanks very
Conrad,
much.
Thank you very much.